Welcome to Lecture 7.7, the two-dimensional heat equation. So let's first outline the steps that we're going to take to solve the heat equation, and then we'll do an example. Okay, so to solve an initial or boundary value problem for the heat equation in two dimensions, i.e. that's this PDE right here, we first find the steady state solution. In other words, set ut equal to 0 and solve for u. That means solve Laplace's equation, which was the topic of the last lecture. And we use the same boundary conditions, of course. And then next, we solve the related homogeneous equation. So basically, we set the boundary conditions to 0, and we keep the same initial conditions. Well, almost the same initial conditions. There's a technicality. Essentially, we subtract off the steady state solution. And we'll see this moving on. Okay, so then we need to add these two things together to get the final solution. This is the theme, almost the theme of the whole class, is that the general solution is the steady state solution, or a particular solution, plus the homogeneous solution. Sort of a picture of this is, so what we're going to have is, we're going to have, say, the heat equation on a region. Let's just say that the boundary conditions look like this. So there's 0 here, and then they're non-zero up here. And then we have some initial condition. And so what we need to do is so this is the general solution. So we need to first solve the steady state solution, and we've seen how to do that. So in other words, find what surface this is. This is going to be some function u ss of x and y. It does not involve t. And then solve the original PDE with 0 boundary conditions. So subtract off the steady state solution from the boundary conditions here, and then we get some, this is, well, that's supposed to be just this thing over here, and then solve this homogeneous PDE. So this is sort of a cartoon as to what we're going to do. Okay, so we've seen how to solve Laplace's equation, and that's what we need to find a steady state solution. So let's do an example of the next step, which is solving a homogeneous PDE. So this is the heat equation here on the left, and on the right, all 4 boundary conditions are 0. So this is a homogeneous boundary value problem. Okay, so to solve this, the first thing that we always do is we assume that the solution separates. So assume that u of x, y, and t. So now we're going to write this as a function of position times a function of time. So let's write this as f of x, y times g of t. Okay? So now we have these 4 0 boundary conditions to deal with, and let's do that now. So these are over here, these are the 0 boundary conditions, again, my own term. So u of 0, y, t equals f of 0, y times g of t. That's equal to 0. So that means, again, this is a function, g of t. And well, this is a function as well, but it's not clear what happens when you plug in 0. This could be a number. Anyways, we know g is non-zero. And so if this is a non-zero function times something is 0, then that better be 0. So f of 0, y equals 0. Similarly, we have 3 more of these. I'll do them quickly. U of x 0 t equals f of x 0, g of t equals 0. That tells us that f of x 0 equals 0. And then similarly, u of pi y t equals f of pi y times g of t is 0. And that tells us that f of pi y is 0. And then the last one is u of x pi t equals f of x pi times g of t is 0, and that tells us that f of x pi equals 0. Okay, so we are going to use these 4 boundary conditions shortly. What else do we have to do? Let's see, we have to plug this thing back into the PDE. So let's actually take these derivatives. So u t equals f times gt, right? We also have u x x. So the x partial of this thing is the x partial, let's call that fxx times g. Because again, we're taking the x partial of this multivariate function times this thing, which is a constant with respect to g. And then similarly, uyy is going to be fyy times g. Okay, so now we're ready to plug this thing back into our PDE. Okay, so ut is, so let's actually write this down. Let's plug back into the PDE. Okay, so ut is f g prime equals c squared times uxx plus uyy, so that's this plus that. So that's fxx g plus fy, oops, let's make that a little smaller, fyy times g. And if you prefer, you don't have to, but you could write this as c squared g times the Laplacian of f. Okay, so now what we have to do is we need to separate variables. So there's different ways we can do that, but remember for one-dimensional PDEs I said divide by c squared fg. Let's do the same thing here. So let's divide by c squared fg, and so c squared fg. We don't really need this term over here, but I'm going to keep it because why the heck not? C squared fg. And now if we do this, look what happens. So we have, so here the f's cancel. So on this side we have g prime over c squared g. And then here we have, here the g's cancel and the c squareds. So we have fxx plus fyy over f, and now I'm not gonna, well, I want to say this thing here, if you prefer, you can write this as Laplacian of f over f, but you don't have to. So now we have separated variables. On the left, this is a function of time. This does not depend on position. And it's equal to this thing, which is a function of position. It does not depend on time. So whatever this quantity is does not depend on time or in position. Therefore, it is a constant. So we call it lambda. So this thing here, this is the eigenvalue equation, as before. Eigenvalue equation. And it gives us, well, let's go up here. Let's see what it gives us. It gives us an ODE in G and a PDE in F. So, so let's see. So we have an ODE. Actually, I'll do the PDE first because I think we're doesn't matter. I think before I've done things in X first. So we have a the Laplacian of f equals lambda f. So Laplacian f equals lambda f, and then we have 4 boundary conditions. And I'm not going to write them, I'll just point up there. Okay, and then the second equation is G prime equals C squared lambda G. Okay, and we don't have any boundary or initial conditions for that. So this is a PDE. Make sure that is a lambda, not that actually looks like a lambda. Yeah. So this is a PDE, a boundary value prob, and this is an ODE. So let me circle that. And right now, let me actually say that we know how to solve the ODE. So note, when you look at this ODE, it should jump out at you. This is an exponential growth or decay. In this case, it's actually going to be decay. So G of t equals some constant a times e to the c squared lambda t. So that's solving for G. And now what we'll do is we'll take a little detour and we will solve this PDE. This is called the Helmholtz equation. Helmholtz, and I think that is, I think I'm spelling it right. It might be TZ, not sure. This is the Helmholtz equation. Actually, I think it is. I think it's Helmholtz. Okay, so we'll have an aside here, and we will solve this boundary value problem that arose when we were trying to solve the heat equation in 2 dimensions. Okay, so no surprise, we're going to solve this using separation of variables. So we're going to assume that the solution separates. So assume that f of x, y is some function in x times some function in y. Big X times big Y. And, of course, we're going to plug this back in and separate variables. So let's do that. So fxx, of course, equals x double prime y, and fyy, of course, equals x y double prime. And now these 0 boundary conditions are going to give us boundary conditions on x and y. So let's do those as well. So these are our 0 boundary conditions, of course my own term. So this is f of 0 y is big X of 0 times big Y of y. That's equal to 0. So no surprise, we've done this a lot now. This is a number, this is a function, equals 0. That number better be 0. So that means that x of 0 equals 0. Okay, next one. I'll run through these quickly. F of pi y equals x of pi times y of y is 0. So again, a number times a function is 0. The number better be 0. So we get x of pi equals 0. We have f of x. I mean, you can probably just fast forward this minute in the tape if you want to, because you know what's coming. Y of 0 equals 0. So a number times the function is 0, so that number better be 0. So y of 0 equals 0. And finally, f of x pi equals big X of little x times y of pi is 0. So y of pi better be 0. And so we are, of course, going to use these 4 things very shortly. Okay, so now let's plug this thing back into the PDE and separate variables, as we always do. So plug back into the PDE. Okay, so fxx plus fyy is this plus that. Let's write that down. So that's x double prime y plus x y double prime equals lambda f, so that this whole thing is lambda times x, y. So there's no c squared in here, so we're not going to divide by c squared times the two functions. We'll just divide by the two functions. So we'll divide both sides by x times y. And look what happens on the left-hand side. Let's see what does happen. So so we get the y's cancel here, the x's cancel here, and then everything cancels there. So so what is that? So that's going to be x double prime over x plus y double prime over y equals lambda. So this is the eigenvalue equation. And I should say that we should probably separate variables. That's really what we've done almost. In the past, we've always put on one side of the equation one variable, on the other side the other variable. So let's actually do that. So I'm going to rewrite this as x double prime over x, and then on the other side of the equation is going to be a lambda minus y double prime. Oops, doesn't quite look like a double prime. Y double prime over y. And now this is a function of x. It is independent of y. This is a function of y. It's independent of x. So whatever this quantity is does not depend on y or on x. So it better be constant. So we call it. Now I can't call it lambda because I have a lambda in here. So let's call it mu. So I'm going to call that mu. Okay, so this is what we get, and this gives us two ODEs. So let's see. So we get a how do I want to write this? So the first ODE is x double prime over x equals mu, and we have these two boundary conditions. And then the second ODE is similar, but involves y. Okay, so how do I want to organize this? Okay, so we get two boundary value problems, and I'll write them down here. So the first one is x double prime equals mu times x, and then we have the x of 0 equals x of pi equals 0. So this is the first one, and we know how to solve this. We have seen this many times before, this boundary value problem. And then the second one is, let's see what that is. That's going to involve y. So that's going to be y double prime equals, now let's see what we get here. So, so how do I want to do this? So this thing here, I'm going to write as y double prime over y equals lambda minus mu. And let me give, since these things are just constants, let me give this another name. Let me call this nu. That's the Greek letter nu. Okay, so I'm going to call this nu. So now I can write this ODE as y double prime equals nu times y. Okay, so nu times y. And this is, and now we have these two boundary conditions right here and right here. Okay, so y of 0 equals y of pi equals 0. So now these are things that we both know how to solve. We know that, let's see, so we know that, how do I want to say this? This is negative n squared, and this is negative, well, it could be different, m squared. So let's write it like this. So the first ODE, x, I'm going to write this as xm of x equals sine of mx, and mu equals negative m squared. And this second ODE is the same thing, just with a different letter. So this is, so y is going to, it might be a different letter, so I'll call it n equals sine of ny, where nu is negative n squared. So these are the solutions to these two ODEs. Again, it's the same thing. They don't necessarily have to be the same m and n, right? There's no reason that they have to be. Any m works for this, and any n works for this. Okay, so let's go back to finding the solution to the Helmholtz equation. Okay, so where were we? So what is lambda? Lambda is up here, and lambda is, so this thing here tells us that lambda is mu plus nu, which is negative n squared plus m squared, or I guess I wrote those backwards, but it doesn't really matter. So lambda is not a negative square, it's a negative sum of squares. Okay? Okay, so to solve this, let's go up to the top. F of x, y. Oh, actually, let me start that over. Okay, so we know that lambda equals negative, now I'll write them, m squared plus n squared. And we know that, and we also know that f, for each pair n and m, we have f, m, n. We have a solution which is sine of mx times sine of ny. So we have sine of mx times sine of my. So the general solution, now we don't really need the general solution because all we needed was a solution for we were solving the heat equation, but we're so close, let's just finish this. So the general solution here, if we were to solve this, we're solved over all n and m, so that this would actually be a double sum. More on this later, this double sum. So bnm sine of, or let me call this bmn just to be consistent, bmn sine of mx times sine of ny. And actually I just realized up above, up here, I should call that sine of ny. Okay, so this is actually the general solution. You may be wondering what I mean by this having two indices. I call this a double sum. More on this shortly. What we really need to take from this is our solution to the boundary value problem that arose on the last slide when we were solving the heat equation. Okay, so let's go back to solving this PDE. So to summarize what we did so far, we assumed that u of x, y, t was some function of position times some function of time. So we plugged this thing back in, and we got two equations. We actually I think I called this thing 1, we got a PDE in f, so lambda, or Laplacian of f equals lambda f, and we got 4 boundary conditions, f of 0 y equals f of pi y equals f of x 0 equals f of x pi equals 0. And then we got this. Then we got the second equation, which was g prime equals c squared lambda g. Which, by the way, now we've solved this. Actually, let me box this right now. I'll say that we actually know what lambda is, so I can do a little better on this. So solving this, we got that lambda was negative m squared plus n squared. We knew, so for every, I'm going to actually do this. I'm going to say lambda mn. So for every pair m and n, we get a lambda that works here. And then we have a solution f of mn of x, y, which was sine of mx sine of ny. So now we can actually take this ODE in G, and I can write this as negative c squared m squared plus n squared G. And so now we know that for every n and m, we get a function of in t. So the solution to this ODE is e, and I'm not going to put a constant in here because I will put one of those in later. So e to the negative c squared m squared plus n squared times t. So these are what we needed to solve this PDE up here. Because now we know for every pair m and n, that are m and n are integers, we have a solution that looks like this times this. So let's write that down. Okay, so u m n of x, y, t equals sine of mx times sine of ny times e to the negative c squared m squared plus n squared t. So this is a solution. Remember how we had a solution for each fundamental frequency for one-dimensional PDEs? For each n we had a solution. Well, we essentially have the same thing, it's just we have 2 dimensions. So we have a fundamental frequency in the x direction and in the y direction. So the general solution, is just the superposition of all of these. So we're summing over all m and all n. So let's write that down. U of x, y, t. And so I think the easiest way to write that down is like this. N and m are greater than or equal to 1. Because notice, these things could be 0, but if either one of these is 0, then the whole thing is 0. So let's just assume we start at 1. And we're going to write f of m n of x, y, times g m n of t. Okay, so what this is the sum. I'm going to actually write this time, just for change of pace, as a double sum. So n equals 1 to infinity, and m equals 1 to infinity. Convince yourself that this is the same thing. That summing up, this is saying over all pairs m and n, we could sum over all n and then over all m, and that we get exactly the same thing. So I'm going to plug this thing back into here, and I'm going to put a constant in front. So bmn times sine of mx times sine of ny times e to the negative c squared m squared plus n squared t. So this is the general solution. What does that mean? That means this represents all possible functions when we all possible temperature distributions as a function of position and time over a square region of length pi, with the condition that the temperature is 0 at the boundaries. So we have sine in the x direction and sine in the y direction. So you can think of this as, so we have fundamental frequencies in each direction. Okay, so what we have not used is our initial condition. So we want not all possible temperatures of this square region, but we want the particular one where the initial temperature distribution is this. And it's hard to sketch what this looks like, but this is going to be wavy in both directions. So it's going to look something like this. Is, I guess, okay. If you want to, you can plug this thing into Wolfram Alpha or your TI calculator, and I'm sure you're going to get something that looks like a bunch of bumps. Okay, but it doesn't matter for now. Let's actually solve, find the particular solution. So what does that mean? So we plug in 0. And we set this thing equal to that. So what the heck is going on here? How do we do that? Let's plug in 0 and find out. So u of x, y, 0. So what happens when you plug in 0 into this thing? So the exponential becomes 1, right? So we just get this double sum of sine of mx times sine of ny. So we get this. Now I'm just going to write it as n and m greater than or equal to 1. This is a sum over all possible pairs of m n times sine of mx times sine of ny. And that thing equals this thing right here. So that's equal to 2 sine of x sine of 2y plus 3 sine of 4x sine of 5y. So in the past, we didn't have these two finite terms like this, but we actually had like a polynomial, x times pi over x. Remember that? So what we did is we said, well, this thing is the Fourier series, and we set it equal to the Fourier series. That was the initial condition. I'm intentionally doing things a little bit different now. So this is already in the form that we want. This is a sine of in x times a sine in y. So look what we have on the left-hand side. This thing here, this is a doubly infinite sum. This is a sum over all, think of it like as a two-dimensional array, over all possible pairs m and n on the left-hand side. Infinitely many, doubly infinitely many of them. On the right-hand side, we just have 2 of them. And we have to equate coefficients on the left-hand side with coefficients on the right-hand side. So this first term right here, this is the 1, 2 term, sine of 1x, sine of 2y. So what that says, that means that this is equal to b1, 2. In other words, the b1, 2 term on the left-hand side has to be equal to the b1, 2 term on the right-hand side. Similarly, this 3, well, this term, this is the 4, 5 term. This is the m equals 4, n equals 5. And the 4, 5 coefficient on the right-hand side better be equal to the 4, 5 coefficient on the left-hand side. So by equating coefficients like we do, this is b4, 5. So what we get is we get that b1, 2 equals 2. We get that b4, 5 equals 3. And then all other Bn or Mn, all other Bmn's are equal to 0. Okay, so how do we write this in a closed form? We don't really have a nice formula for these. We just have two cases. Well, when you plug this back into this double infinite sum, all of the terms are equal to 0. Well, except two of them. So let's just write out our final solution as two terms. Let's write the B12 term times the B45 term. So let's do that up here at the top. So u of x, y, t equals, actually let me give myself a little more space for that. I'm going to go up a little bit. So u of x, y, t, really all we get is B12 times F12 x, y times G12t plus B45 times F45 times xy times G45 times t, because all of the other terms are 0. And so what is this? This is B12 is 2 times sine of x sine of 2y times e to the, now what, e to the negative c squared times m squared plus n squared. So that's 1 squared plus 2 squared, which is 5, right? T to the negative 5c squared t. And then this term is going to be B45, which is 3. So that's going to be 3 times sine of 4x times sine of 5y times e to the negative c squared times, now what's m squared plus n squared? So that's n squared is, or m, that's 16 plus 25, that's 41, right? So that's negative 41c squared t. Okay, so this is our particular solution. That satisfies the boundary conditions and the initial conditions. So this is our solution to the heat equation, given these boundary value problem, or given these boundary conditions and this initial condition right here. Notice what happens over time. As time goes to infinity, the exponentials will die off. This one quicker than that one. And so the steady state solution is going to be 0. And that makes sense because we have a square region where the boundary is held fixed at 0 and heat dissipates and it can escape, and it will, of course, approach what you get if you take this square wire and plug it into a soap bubble. You will get the 0 solution. Okay, so let me finish with an inhomogeneous example, and this is very similar to two of the problems that we have seen recently. So this is the heat equation. Here we have 3 boundary conditions are 0, and the fourth one is non-zero. We've seen this before. So the boundary looks like this. It's a square, and then on the back we have something that looks like that. And let me sketch this. Something like that. Maybe I didn't do a very good job, but I think you know what this looks like. This, of course, is in the x direction, and this is in the y direction. And by YSS here, let me just tell you what it is before I go over it in much detail. So this is just shorthand for YSS of x, y. So by this I just mean this surface here. So the solution to Laplace's equation. So that, recall that we've actually seen this. This is n equals 1 to infinity of 4, 1 minus negative 1 to the n over pi n cubed times sinh of n pi times sine of n x times sinh of n y. And so the actual equation isn't as important as much as just this is the steady state solution to this thing here. Okay, so if we were to solve this, one thing we could, well, let me actually just tell you the solution first. So the solution to this is, of course, the steady state solution plus the solution to the homogeneous equation, x, y, t. So let's actually write out what this is. Now we have solved the homogeneous version of this. That was example 2a. We just did that. So actually, let me do the steady state first. So this thing goes down here. So this is n equals 1 to infinity of 4 times 1 minus negative 1 to the n over pi n cubed times sinh of n pi times sine of nx sinh of ny. So there's that. And then we have to add the homogeneous solution, which is example 2a, and that is, so that's 2 sine of x sine of y times e to the minus 5 c squared t plus 3 sine of 4x sine of 5y, it's supposed to be a 4 there, e to the negative 41 c squared t. That's the 41. Okay, so this is the solution to this inhomogeneous PDE right here. So it's the steady state solution, which we did in the previous lecture, plus the homogeneous solution, which we just did in the previous example. And if you're curious as to why this thing had to be here, I'm not going to go over it in detail, but if you wanted to, you could change variables, and you could do something like let v of x, y, t be equal to u of x, y, t, and subtract off this steady state solution. So that's, you could subtract off that, which I'm not going to write it as this, I'm just going to leave it as this. And so what you're doing is you're taking the solution to this inhomogeneous problem and you subtract off this little bump here, and then what you get, if you write out the boundary conditions, you get the same PDE, because all the derivatives are going to be the same. These things are going to be 0. This boundary condition, you're taking this thing and you're subtracting off that, so you're going to get 0. And the initial condition is going to give me, I subtract off this, and my initial condition is going to be just this thing. So now, if you do this, the PDE in V, when I say the PDE, I mean the initial value, initial and boundary value problem, is precisely example 2a. So really what we're doing is we're saying, so as a little cartoon of this, we want to say here's the boundary, here's the temperature at the boundary, here's the boundary value problem, and so we have this initial heat distribution, and the solution to that is just the steady state solution plus making it homogeneous and then solving that equation. So this is example 2b, and this is, this first one was last lecture, 7.6, and then this thing here was with the same equation, just with 0 boundary conditions, so this is example 2a. So this surface is, so think of it as taking the previous example and the general solution, which was, or the particular solution, which was this thing, and just bumping it up by this thing, just adding these things together, and that's the solution to this equation right here.